Hi friends, welcome to Acaspirants, the vision to reality, the knowledge platform. We welcome all of you to our first video in chemistry. Enjoy the session, stay tuned with us to be an aspirant. Hello everyone. In this video, we are talking about the structure of a benzene. So before getting into the topic, this session is divided into small topics. Number 1. Benzene and introduction. Number 2. The structure of benzene. Number 3. Kekulé structure of benzene. Number 4. Hybridization of carbon in benzene. Number 5. The resonance and stability of benzene. Let's find out. First, benzene. The molecular formula for benzene is C6H6. Benzene is an aromatic compound and it exists as an oily liquid which is used as a solvent in many industries. Benzene is a liquid hydrocarbon which belongs to a large family of organic compounds known as aromatic hydrocarbons. Now, the term aromatic hydrocarbons, I'm dividing it into two major terms, aromatic as well as hydrocarbons. First one, aromatic. What do you mean by aromaticity? The word aromatic is derived from the Greek word aroma, which means pleasant smell or characteristic sweet smell, which means aromatic compounds have a general characteristic smell. Each aromatic compound has its own characteristic pleasant smell. Next one, hydrocarbons. Hydrocarbons may be defined as the binary compounds containing carbon and hydrogen, or hydrocarbons may also be defined as the covalent hydrides of carbon. Now, hydrocarbons as the binary compounds of carbon and hydrogen. In hydrocarbons, carbon and hydrogen only present and the bonding between carbon and hydrogen are purely covalent. That means in covalent bonding, sharing of electrons takes place. Number 2. The structure of benzene. From elemental analysis and molecular weight determinations, the molecular formula for benzene is found to be C6H6. Now, we are comparing the molecular formula with the general formula for alkanes, alkenes, and alkynes as well. The general formula for alkanes is CnH2n plus 2. So substituting the values, we get C6H14, which is hexane, and it doesn't match for benzene. Next one, the general formula for alkenes is CnH2n. Substituting here, we get C6H12. That means hexene. So it doesn't match with benzene. And also this general formula suits for cycloalkanes as well. So benzene is not a cycloalkane. Next, the general formula for alkynes is CnH2n minus 2. So substituting here, we get C6H10. That means it's the molecular formula for hexane. So it doesn't suit with benzene. But this molecular formula indicates a high degree of unsaturation. Now, what do you mean by unsaturation? Unsaturation is nothing but in a covalent molecule the presence of double bonds and triple bonds are known as unsaturation. Especially in hydrocarbons, the bonding between carbon atoms is specified. If the bonding between carbon atoms is single bond, then it is a saturated bond. If double bond exists between carbon atoms, then it is unsaturated. Similar is the case for triple bond. It is also unsaturated. In short, benzene is an unsaturated molecule. So, from our previous knowledge, it is found that benzene is an unsaturated molecule. So, we don't know whether the molecule possesses a double bond or a triple bond. Here, the presence of 3 double bonds in benzene was found out. Benzene was found to be a stable molecule and found to form a triozonide, which indicates the presence of 3 double bonds. As indicates in the figure, here we can see benzene ring. In that ring we can see alternative single bond and alternative double bond as well. And each carbon atom is bonded to each hydrogen atoms. And the benzene is a closed chain structure. Number 3. The Kekulé structure of benzene. The structural formula for benzene was suggested by a German chemist. His name is Friedrich August Kekulé. He was the mastermind behind the structure for benzene. He was born in Darmstadt, Germany. And we will discuss how he found out the structure of benzene, and there was a story behind it. So please listen carefully. What was the story? Kekulé described the discovery of benzene structure later as he was sitting writing at his textbook, but the work did not progress. His thoughts were elsewhere. He turned his chair to the fire and dozed. Again the atoms were gambling before his eyes. Long rows, sometimes more closely fitted together, all twisting and turning in snake-like motion. One of the snakes had seized hold of its own tail, and the form whirled mockingly before his eyes. He suddenly woke up and drew the structure of benzene as a closed hexagonal ring which comprises of alternative single bond and alternative double bond, as mentioned in this picture. Number 4. The hybridization of carbon in benzene. The atomic number of carbon is 6. The electronic configuration of carbon is 1s2, 2s2 and 2p2. Below that we can see a box diagram of orbitals. First one, we can see carbon atom in its ground state. In ground state, the electronic configuration is found to be 2s2 and 2p2. After the absorption of energy, the carbon atom goes to excited state. In excited state, the electronic configuration of carbon, that means C star, becomes 2s1 and 2p3. As you can see there, 2 of the 2p orbitals and 1 2s orbital undergoes sp2 hybridization to become an sp2 hybridized orbital, as mentioned in this picture. We get a trigonal planar geometry. Now the bond angle between two bonds is found to be 120 degree, because we can note that sum of the angles around a point is 360 degree. So dividing 360 by 3, we get 120 degree. And we can see an electron which is included in dotted or dashed orbital lines that indicates the non-bonded electron or the free electron, and that free electron is responsible for the pi bonding. We will discuss in this video later about pi bonding in benzene ring. Number 5. Resonance and stability of benzene. From chemical bonding and molecular structure, that means chapter 4 class 11, I hope you have learned about resonance. It describes the stability of a molecule. That means if a molecule or a species possesses more than two reasonable structures, then the molecule or that species found to be more stable. It is applicable to molecules, ions, radicals, as well as functional groups. Here, structure 1 and structure 2 are the resonance structures of benzene, or we can see that structure 1 and structure 2 are the canonical forms of benzene, and structure 3 is the resonance hybrid, or in short we can say it is the actual structure of benzene. In the actual structure of benzene, we can draw a complete circle inside a regular hexagon or a dotted circle inside a regular hexagon. From the previous slide, it is evident that the three double bonds in benzene are not fixed. In other words, the double bonds in benzene are delocalized pi bonds. And what are pi bonds? If a double bond exists, there is a presence of single sigma bond and a single pi bond. In triple bond, there is a single sigma bond and two pi bonds. So here all the sigma bonds are fixed and the pi bonds are delocalized. We will discuss about the delocalization of pi bonds later in this video. Keep watching. In this slide, we are going to calculate the number of sigma bonds in benzene ring. From this picture, we can see 6 purple colored p orbitals, and each p orbital represents the p orbital of carbon atom non-bonded in the benzene ring. Now, we can see numbers 1, 2, 3, 4, 5 and 6. Each number represents each carbon atom. Now, carbon atom C1 and C2 bonded by one sigma bond. C2 and C3 are bonded by one sigma bond. C3 and C4 are bounded by one sigma bond. C4 and C5 with a sigma bond, again C5 and C6. Similar is the case for C1 and C6. So total number of sigma bonds inside the ring is 6. Now we can see extended line segments from each vertex of the benzene ring. It represents the bonding of each carbon atom with each hydrogen atom. The bonding between carbon and hydrogen is sigma bond. So total number of sigma bonds in carbon-hydrogen bond is again 6. So total number of sigma bonds in benzene equals 6 plus 6 gives 12. Next we are going to calculate the number of pi bonds in benzene ring. From previous knowledge, we can say that the double bonds or the pi bonds are delocalizing in nature. That means the double bonds are not fixed. That's the reason why we have two resonance structures for benzene. Here, structure number 1, carbon atom C1 is bonded to carbon atom C2 with a pi bond. Here the pi bond is represented by two lines, one connecting both the upper lobes and the other one connecting two lower lobes. Similarly, C3 is connected to C4 through a pi bond, and C5 is connected to C6 through another pi bond. So total number of pi bonds in structure 1 is 3. Now, as we have mentioned earlier, these three double bonds are not fixed. It keeps on oscillating. So in structure 2, C1 is connected to C6 through a pi bond. C2 is connected to C3 through a pi bond, and C4 is connected to C5 with another pi bond. And the bond line representation for each resonance structures are shown below the orbital diagram. It is known that the pi bonds are delocalized in nature. Now we are going to deal with the delocalized pi electron cloud of the benzene ring. From X-ray diffraction methods, it is evident that the distance between each carbon atoms are found to be equal, and benzene possesses a regular hexagonal ring. The upper lobes of all the p orbitals are fused together, and the lower lobes of all the p orbitals are fused together separately to give a structure like a donut structure in the right hand side of that slide. As you can see there, the hexagonal ring is sandwiched between two rings or two donut rings of electron cloud. It shows that benzene is a planar molecule. It's all about the structure of benzene. I hope this video is informative. Thank you for watching.